All right, good morning. I think that this is rolling. So I wanted to go over number 2C with you guys this morning. Hopefully you guys are working on this in the morning today and not putting it off until the weekend. But if you did, hey, it's weird times, so no judgment from me. But anyway, so number 2, Lemon and I kind of anticipated this might give you guys some trouble, so we thought this would be a good video pointer to kind of dig into the bones of it and the explanation of it. Now, I don't want you guys to worry. How was I supposed to come up with that? I don't think we're at that stage right now where it's like you're supposed to come up with all this on your own. What I want you to do is just to check: am I understanding each of these steps that Dielman's going through? So in number 2, what we have is we've got the engine that has a diameter of 7 centimeters, and we've got the rear axle that has a diameter of 10 centimeters. So when I think about first, what's the relationship between the two of them? Well, the engine sprocket, one rotation of the engine sprocket is obviously going to occur at a more rapid pace than the rotations of a rear axle because the rear axle is bigger. So it's going to take longer for the rear axle to rotate than it will the engine sprocket. So right from the start, we know that one revolution, or I guess you could say the angular velocity, rotations per minute, of our rear axle is going to be 7/10, right? 7 divided by 10, 7/10 the angular velocity of the engine sprocket. And that makes sense because the engine sprocket's going at a faster angular velocity. It's rotating, it's got a higher RPM because it's smaller than the rear axle. So the rear axle is going to be only 7/10, so less than 1. So it's not the same pace and it's not more. But then also we know that the rear wheel has a diameter of 28 centimeters. The rear wheel is directly, just similar to the bike, the rear wheel is directly related to the rotations per minute of the rear axle. And that'll come into play in part C. So part C, when rounding corners, a speed of 30 kilometers per hour or less is needed to reduce lateral sliding. And what's the engine speed? So they're giving us a linear velocity of the rear wheel, and they're asking us to come up with an angular velocity of the engine. Where do we go from here? So my key question, which engine speed in RPMs is optimal for a go-kart going 30 kilometers per hour around a corner? Well, first we need to remember that the general definition, linear velocity equals angular velocity times the circumference of the wheel. So what of this equation do we know? Well, first, linear velocity, right? That's our distance, how far we're going at per minute or per second or per hour. Angular velocity is how many rotations we have. So if we know the circumference of a wheel, if we were to like unravel the wheel and make it into a flat line, that would basically tell us how far we are going distance-wise, and then how many rotations would be, all right, how many of that single distance we can go with one wheel rotation. All right, well, how many rotations are we going per minute? That's what our angular velocity is telling us. So if we multiply those together, it tells us the total distance. If you want a more in-depth explanation of this relationship, go to my YouTube channel and look at the Investigation 2.1, number 1 through 3 explanation. Okay, so now what do we know? Well, we don't know, so we've got this unknown variable x for the engine speed, and that's our angular velocity in RPMs. However, what we do know is that the circumference of the rear wheel in kilometers. Now, why are we doing it in kilometers? Well, we're doing it in kilometers because the 30 kilometers per hour, they're giving that to us in kilometers. So we need to convert everything to kilometers. So they tell us that the diameter, so over here on the right, they tell us that the diameter is 28 centimeters for the back wheel. So equivalently, that would be 0.00028 kilometers. So when I'm trying to find the circumference, it's pi times diameter. Well, my diameter in kilometers is 0.00028 times pi. And then last but not least, our linear velocity is 30 kilometers an hour, and that's what they told us ahead of time. So we've got 2 known and 1 unknown. We plug this into our equation and we can solve it. So first, I'm going to plug it in the same way I see it up here. Linear velocity equals angular velocity times circumference of the wheel. So we've got the linear velocity of 30 kilometers per hour, and that is equal to the angular velocity, which is in rotations per minute, which is unknown, times the circumference of the wheel, which we said was 0.00028 times pi, right up here above. Now, a note, I circled RPM and I circled hour because on the right side of our equation, we're using the unit of time of minutes, and on the left side, we're using hours. And so how do we convert minutes into hours? We need to use some type of conversion. And so I have to add something to this right side of my equation so that it is equivalent to hours. Because again, this is our anchor here, 30 kilometers per hour. That is our main given piece of information. And then we need to use that to determine our engine rotations per minute. So now on the right, we're minutes. On the left of our equation, it's measured per hour. So we fix this by multiplying both sides by 60 because there are 60 minutes per hour. So I'm going to revise my equation. I've got 30 kilometers per hour still, and that's our linear velocity. That equals our angular velocity of x RPMs for our engine times the circumference, and then I'm multiplying that by 60. From here, it's just a simple, we're just solving for x, and so I multiply 0.00028 pi times 60, and that gives me 0.052779. I'm trying to isolate the x, so I'm going to divide both sides by that decimal. And so when you do 30 divided by 0.052779, we're left with just x RPMs on the right side, and we've got 568.4. So this is the RPMs for the wheel. I want you to remember that. We calculated the RPMs for the wheel because this circumference is the circumference of the rear wheel. What are we trying to find again? Our big question. Which engine speed in RPMs? So we found the RPMs for the rear wheel, which corresponds to the RPMs of the rear axle, but that didn't give us the RPMs of the engine. So this number is right in the sense that it's the RPMs but for the wheel. So how could I convert this to RPMs for the engine? Well, remember that relationship we talked about at the beginning. The angular velocity of our rear wheel or axle is going to be 7/10 the angular velocity of my engine. So if I set up another little equation, 568.4 RPMs, that's the angular velocity of our rear axle and wheel, that should equal 7/10 or 0.7 times my engine angular velocity, which again we don't know. So if I want to try to isolate the engine RPMs, I'm going to divide both sides by 0.7. And when I do 568.4 divided by 7, I get 812, excuse me. So I put a bunch of boxes around that because that is our official final answer. So now, what are a couple of items that we needed to know here? Well, we needed to know some basic conversions, right? How do I convert something from minutes to hours? How do I convert centimeters to kilometers? How do I convert rear axle rotations per minute to the engine rotations per minute? So it's all about what's the relationship between the items I'm working with. That is, I think, the part you got to be super neat and orderly about. Using labels, not just numbers. So you'll notice here I've got kilometers per hour, RPMs, and I kind of set things up ahead of time so I know what I'm doing and what each piece is, and so that in the end, right here, it looks a little vague. 568.4 equals X RPM. For most of us, myself included, I probably would have said that's my answer because it's X RPM. But you got to remember that where are these numbers coming from? The 0.00028 pi, that's the diameter, that's the circumference of the back wheel. That is directly related to the rear axle, not the engine. So just a couple of important things just to remember. But yeah, your final answer would be 812 RPMs. Feel free to please rewind, rewatch, pause, study the numbers, whatever you got to do to make this stick. But for 2C, that is my help for you guys. Thanks, guys. Have a really good weekend. This first week was a little bit a bit of a test, and so next week we will jump right in. See you guys.